What's up everybody, and welcome to part 5 of my Basics of Deep Learning series. In the previous video we left off with the observation that to speed up our code we need to vectorize it using a Python library called NumPy. And this is what we're going to do in this video. So let's get back to the notebook, and here we're going to scroll up to the beginning of the notebook to implement NumPy. So we're going to say import NumPy as NP. And now we want to vectorize how we determine the output of one neuron. So let's copy this heading and then gonna paste it, and here we write then colon vectorized. And now to get rid of this for loop here, we simply can replace this weighted sum function with the built-in NumPy function that calculates the dot product, because as I said before, the weighted sum and the dot product are equivalent. So we can basically just copy these lines here and then paste them, and then instead of writing weighted sum we say np dot dot. That's the function that calculates the dot product. And now before we can actually run the cell, we obviously have to transform those inputs and weights into vectors. And the way we're going to do that is simply by transforming these Python lists here into NumPy arrays. So we're going to say inputs equals np.array inputs, and then weights equals np.array weights. And now if I run this function here, we should get the same results as before. So let's see if that's the case. And it is. So with that, now we have vectorized how we determine the output of one neuron. So now let's vectorize how we determine the output for the whole neural net. So let's copy this heading again, and then we're gonna paste it, and again we write colon vectorized. And now to vectorize our determine layer outputs function and thereby to get rid of those two for loops, let's recall what the function does given what we now know about the dot product. So what we do in this function is basically simply loop over all the examples, and then for each example we loop over all the weights, and then we calculate the respective dot products. So basically what the function does for the case here where we don't use the activation function is to calculate all the possible dot products between this list of lists and that list of lists. And as it turns out, there's actually a linear algebra operation that does exactly the same thing, and it's called a matrix multiplication. It is, however, slightly different defined. Namely, instead of using this row here in the second list of lists, or in linear algebra terms in the second matrix here, we're gonna use the column vector. So we're gonna have to transform our weight matrices in such a way that the rows become the columns. And I think the reason why matrix multiplication is defined this way is because that way the intersection of those vectors here indicates where the result of that dot product is going to be stored in the resulting matrix. So for example, if you want to calculate the dot product of this first row and the second column, then the result is going to be in the first row and second column. And if you want to calculate the dot product of the third row and the first column, then the result is going to be in the third row and first column. And if you do the calculations in this way, you don't have such a nice representation. And this way of defining the matrix multiplication leads to a certain condition that needs to be fulfilled, namely the number of columns in this first matrix here must match the number of rows in the second matrix. Otherwise you couldn't calculate the dot product. So let's say, for example, that this matrix here would have 5 columns. Then you could multiply this element with that, this with that, this with that, and this with that, and this last element here wouldn't have a corresponding element in the second matrix. That's the reason why the number of columns in this first matrix has to match the number of rows in the second matrix. And an easy way to remember this condition is to simply write down the dimensions of those matrices. So for example, this first matrix is a 3x4 matrix. It has 3 rows and 4 columns, and the second matrix is a 4x2 matrix, 4 rows and 4 columns. And now to check if we can multiply this matrix with that, you simply look at those inner numbers, and if they are the same, then you can do the matrix multiplication. And the nice thing then also is that those 2 outer numbers here, they indicate the dimensions of this resulting matrix, because this has 4 rows and 2 columns. And for the case where this matrix had 5 columns, here those inner numbers don't match up, and so you can't multiply this matrix with that. So that's how matrix multiplication generally works. And as always said before, to make use of it in our code, we now have to transform our weight matrices in such a way that the rows become the columns. And here I have already done that, and I've also transformed the inputs and weights into NumPy arrays. So let's copy that, and then we're gonna paste this. And in my opinion, this here is the better way of representing those weight matrices, because if you look back at our diagram, and if you now transform this weight matrix into this representation, then now you can basically read this weight matrix as the weights going from a certain node in the previous layer to a certain node in the subsequent layer. So for example, this weight here goes from node 3 to node 1. So in the matrix, it's this value. It's the weight going from node 3 to node 1. And another example, this weight here goes from node 1 to node 2. So in the matrix, it's this value. It's the weight going from node 1 to node 2. And this from to representation is what I meant in one of the previous videos when I said that the underlying structure of the weight matrices is also easy to remember, because all you have to do is look at the neural net and then count the number of nodes from which the weights are coming from, and then count the number of nodes to which the weights are going. So for example, in this case, the weights go from 4 nodes to 2, and hence the matrix is going to be a 4x2 matrix. And now with that we can finally vectorize this determine layer outputs function, and all we have to do is to simply use the built-in NumPy function that calculates the matrix multiplication. And actually there are 2 such functions. One is called matmul, and the other is somewhat surprisingly also np.dot. And for 2D arrays, those 2 functions have the same behavior, and since in most tutorials np.dot is used, that's what we're also going to use here. So we're going to say hidden layer inputs equals np.dot inputs and weights 1, and then let's also print that. So hidden layer inputs, and let's run this now, and as you can see, we get the same results as before, as in this diagram. So with that, now we have vectorized our determine layer outputs function, and we've got rid of those 2 for loops. So now let's get back to the graph where we plotted the average runtime of our determine layer outputs function. And now let's see how the NumPy implementation compares to that, because after all, that's why we vectorized our code. And here is the graph for that. And as you can see, the NumPy function is much faster than our Python implementation. It even looks like that it doesn't get any slower. But if I just plot this line here, then you can see that the average runtime also grows exponentially. But here, for this 400 by 400 matrix, the np.dart function only needs about a millisecond, whereas our function needed more than 3.5 seconds. And this difference right here is, in my opinion, the main reason why linear algebra is used in deep learning. At least I haven't seen a tutorial yet where someone said something like, okay, what the dot product tells us is how similar two vectors are in the terms of the direction they're pointing into, and this is how you can interpret it in the context of deep learning. And besides this speed improvement, another advantage of vectorizing the code is that it makes the code much more succinct and therefore much more readable. So for example, here you can immediately grasp what's going on in this line, whereas in our function you really have to dig in to understand what's going on. So now, obviously, to determine the output of the neural net, we have to put these hidden layer inputs into our step function. And the way that we define it, however, is that it expects a number as a parameter. So now we have to go on to define it in a new way so that it can handle NumPy arrays. And the way we're going to do that is that we take the array, so for example, the hidden layer inputs array, and then we say is bigger or equal to 2, which was the threshold level of our step function. And this then gives us a Boolean array where all those values are evaluated based on this comparison. So for example, since this value is below 2, or it's not bigger or equal to 2, that's why we get a false here. And now obviously we want to have zeros and ones in this array. So we're going to put this expression into parentheses, and then we write dot as type int. And this will give us then an array of zeros and ones. So this is how our new step function is going to work. So let's define it now. So I'm going to say step function, and then we put in an array, and then we say return parentheses array bigger or equal to 2 dot as type int. And that's our new function. So now let's determine the hidden layer outputs. So we say hidden layer outputs equals step function of the hidden layer inputs, and then we're also going to print that. So hidden layer outputs, and now let's run this. And now, as you can see, we get the same result as in this diagram. So now let's determine the output for the whole neural net. So we're going to say output layer inputs equals np.dart, and then hidden layer outputs, comma weights 2. And then let's also print this output layer inputs, and then we're going to say output layer outputs equals step function of our output layer inputs, and then we're also going to print those. So let's run this now, and as you can see, we get the same result as before. So the first flower is again predicted to be in Iris setosa, the second Iris versicolor, and then the third Iris virginica. So with that now, or this is now how you can implement the feedforward algorithm. And I know now I've basically spent 3 whole videos explaining just basically 4 lines of code, but I simply want to make sure that you really understand every detail of what's going on in these lines. And to really make sure that that's the case, let's now visualize what's going on in these lines. So here I have again depicted the upright neural net, and here is our code. So what we're going to do in this first line here is to multiply our inputs matrix with weight matrix 1 to get the hidden layer inputs matrix. So in the neural net, what we're doing is we multiply these inputs here with those weights to move from here to here. And then to move through the nodes from here to here, we simply apply our step function to this matrix. And then in the next step, to move from this point in the neural net to this point, we use the hidden layer outputs and multiply them with weight matrix 2. This will then give us the output layer inputs. And then finally, to move again through the nodes from here to here, we simply apply our step function to this matrix. And this is now then our output of the neural net, and this is how the neural net makes a decision. And now, before I conclude this video, I want to make you aware of another effect that you need to consider, or another aspect that you need to consider when implementing the feedforward algorithm. And that is the non-commutative property of matrix multiplications. And what it means is that if you have a matrix A and a matrix B, then multiplying matrix A with B is not the same as multiplying B with A. And that's because you're using completely different values to calculate those respective dot products. So for example, to calculate this dot product, you use this row and this column, and to calculate this product, this dot product, you use that row and that column. So the numbers are completely different, and hence the resulting matrices must be completely different. So the order in which you multiply the matrices matters. And why that's important is because you have to be careful in what order you put in the inputs and the weights into this np-dot function. I mean, in this case, for example here, it wouldn't hurt you that much if you accidentally switched up the order. So if you would say np-dot weights 1 and then inputs, because in this case you would simply get an error, and that's because the shapes of those matrices are not aligned. So those inner values here, they don't match up. And you could get around this by using the transposes of these matrices, but I wouldn't suggest doing that, because this simply makes things unnecessarily complicated. So for this particular scenario here, the non-commutative property of matrix multiplication wouldn't hurt you that much. But let's say we would have two symmetric matrices. So we would have, for example, two input values and two hidden nodes, and then two examples. So we have two 2x2 matrices. And if you would now do the calculations correctly, you would multiply this matrix with that to get this matrix, and this then you put into the step function to get these outputs. And if you now switch up the order, so if you multiply this matrix with that, then you get these results, and as expected they are completely different. And also, if you look at what values you actually multiply and add up to get these values here, you will see then that those calculations don't make any sense at all. So for example, to calculate this value, so the input of this node, you use this row and that column. So you multiply this value, which is this weight here, with this value, which is the first feature of the first example, and to that you then add this value, which is this weight, times this value, which is then the first feature of the second example. And as you can see in this diagram, you actually want to calculate the input of this node, but you are using those weights. And obviously this doesn't make any sense. So the neural net couldn't possibly make any correct predictions. So to not fall into this trap, you really have to make sure that the inputs and the weights are stored in the appropriate formats. And what I mean by that is that the inputs should be stored in such a way that the rows represent the examples and the columns represent the features. And this condition is in most cases fulfilled because that's how you typically store the data. The more important thing that you need to consider is that the weights are stored in this from to representation, because then you can simply look at the neural net and implement the feedforward algorithm, because here too the inputs become for the weights. So you can then simply write np inputs and then weights 1. Then to get the output for the whole neural net, you simply then write hidden layer outputs and then weights 2. So as a word of caution, when you look at other code examples, you should make sure that you understand how the inputs and the weights are stored. So now with that, we have now basically answered this first question of how the algorithm makes the decision, and now we can start to tackle this second question, which was how do you determine the right parameters for the algorithm. So in the case of deep learning, how do we find such weights that the neural net is able to make correct predictions? And this will be the topic of the upcoming video. So thanks for watching, and hopefully I will see you in the next video.